Hey guys, welcome. Yeah, so a really fun, cool video, and I suppose the best place to put this is in fun, challenging algebra series, but yeah, this is really number theory or contest math. So the discussion here is going to allow you to not just answer this question, but also answer this question for any natural number n. And so this is something that, you know, is frequently useful in number theory and, again, in contest math. Yeah, cool. So with that said, let's get started. Now, I'm going to answer the question, but let's demonstrate the method on just 360. Yeah? Okay, now, the method starts by figuring out the prime factorization of whatever number you're given. So here we're saying that the number we're given is 360, and the prime factorization of 360 is going to be what? Like, well, it's 36 times 10, so if we process it that way, we know 36 is 4 times 9, so that's 2 squared times 3 squared. That's the 36th part, and then we need times 10, so times 2 to the first, and then times 5, right? So what we have in that is 2 to the third times 3 squared times 5 to the first. Now, notice that for any natural number n, we're guaranteed by unique factorization theorem in number theory that we can factor whatever natural number n into a product of primes unique to a power. Yeah? So we can write it like, you know, some prime p1 to some power alpha 1 times p2 to some power alpha 2, and all the way to like times some p sub n to some power alpha sub n. Now, let me explain the unique to a power part of the uniqueness guaranteed by the prime factorization theorem. So it's unique to a power because, like, if n is 50, right? The prime factorization of 50 would be like 2 times 5 squared, 2 times 25. Whereas if n is 100, then the prime factorization is 4 times 25, so that's 2 squared times 5 squared. Now, if we're only considering the prime factors, both 100 and 50 use the two primes 2 and 5, right? So that's not unique, they use the same two primes. But the guarantee is unique to a power. And by that, in fact, we're seeing it, which is that, like, yeah, the factorization of 50 and 100 is unique by the difference in power on the prime 2, right? Yeah. Okay, cool. But the point is that, like, we're able to, using this theorem, factor any number that we're given as a product of primes to some powers, right? Okay. But remember, the question we're trying to answer is how many factors some natural number n has, right? So this is what you do. So first, you figure out the prime factorization of whatever number you're given. So for 360, we're done with that. And then to figure out how many factors the given number has, all you do is add 1 to each exponent on the prime factors. So in this case, 3 plus 1, and then 2 plus 1, and then 5 plus 1. Oh no, sorry, 1 plus 1. My bad. So what you do is add 1 to each of these powers on the prime factors. So this is, the 3 plus 1 is from there, and the 2 plus 1 is from here, and the 1 plus 1, and obviously I'm repeating myself because of that little, like, mistake I made in writing a 5 there, but yeah, you get it. So now this is 4 times 3 times 2, right? Okay, so what's that? That's 4 times 6, and what? No. Yes. 4 times 6, which is 24, right? Yes. So supposedly 360 has 24 factors. Now, it's kind of hard to list all 24. It's not hard, it's just like tedious. So let's use this method on the number 36, and then let's verify that it works by listing the factors of 36. So the method, again, begins by figuring out the prime factorization of 36, which is 2 squared times 3 squared, 4 times 9. And then we take these exponents and add 1 to them. So that's 3 and then 3, and then we multiply after we add 1 to each of the exponents, right? So this is 9. So supposedly 36 has 9 factors. Our question is to answer how many factors, right? Okay, well, for 36, it's small enough that we can list them. So we begin with 1. That's a factor of 36. And then 2, 3, 4, 6, 9, 12, 18. And once you get to half of the number, the next factor has got to be the number itself. And so 36. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. Done. No. Yeah, that is 9. But we're not done because, remember, we love math. And so we want to understand why this works. So this is why it works, right? Like, 2 and 3 are the ingredients for any factor of 36, right? So 2 and 3 are the ingredients. We have to cook with them to make any factor of 36. And what we're allowed is to use 2 to the 0, 2 to the first, and 2 to the second. We can't have more than 2 to the second, because that's the most that we see in the factorization of the number itself. And then for 3, we similarly have 3 to the 0. So in writing 2 to the 0 and 3 to the 0, what I'm saying, well, let me explain with the 3 to the 0 is like, well, a certain factor of 36 may not use any 3's. For example, 4 is a factor of 36, and it's 2 to the second times 3 to the 0. It doesn't use any 3's. Yeah? Okay. So 3 to the 0, and then 3 to the first, and then 3 to the second, right? And so now you should understand why we add 1 to each of the powers, because, well, there are 3 possible powers of 2 we can use, and 3 possible powers of 3 we can use to cook up some factors of 36. And so we have a total of 3 times 3, or 9 possible factors. And so like, for example, we can use 2 to the 0 and 3 to the 0. That's the factor 1. And we can use 2 to the 0 and 3 to the first, and then 2 to the 0 and 3 to the second. So, like, you know, the factors 3 and 9 and 1 don't use any powers of 2, right? Okay, and then we could send this, and so now this should reveal why we multiply once we figure out all the possibilities for each of the prime factors to powers. Yeah? Okay, that was a lot of hand gesture. Okay, I'm done. Yes, I know. I didn't answer the question, but don't you get it? Don't you get it?